Alright, yeah, I'm sorry.
J'ai oublié les connexions.
There we go. Okay, here we go. Hello everybody, my name is Jose Gomez. I am currently an upcoming senior at the University of Michigan, and I will be speaking on behalf of Michigan's Autonomous Aero Vehicles team about our approach to this year's International Aero Robotics Competition. So just to start with an overview of the problem statement, we've been charged with designing a vehicle that is capable of coordinating a fleet of ground vehicles. The vehicle has to be able to navigate in an open environment and direct 7 of the 10 ground vehicles across the goal line. And it also has to be able to avoid dynamic obstacles in the environment. And of course, all this has to be accomplished autonomously. So the way this presentation is going to go, first I'll present our vehicle and talk about the structural design aspects. Then I'll demonstrate some of our durability tests, talk about the flight controls, obstacle avoidance algorithms, localization algorithms, and then our strategy for this year. So we'll start with the airframe. This year it's 620 grams, which is significantly heavier than past iterations, and that's because there's no longer a mass limit on the vehicle. It's a custom carbon fiber design with a heavy focus on durability and modularity. So not only is the vehicle less prone to brakes, but when it does break, it's very easy to switch parts out rapidly without disassembling the entire vehicle or reconstructing the entire vehicle. So the modularity helps with repair jobs, but it also means that it's rapidly manufactured. So the production process is increased like tenfold from previous iterations. Another major design in this year's vehicle is the prop guard. Prop guards are key to safety, but also to durability. Without a prop guard, if you bump into a wall, your prop will probably snap right there and you're out of the air. But a prop guard means you're a little bit more forgiving of that. Because it's carbon fiber, it's stiff enough, because of the ribs that we put in, to not deflect into the prop just without any effort. But it's still elastic enough where if you bump into a wall, there's an elastic reaction and it actually bounces off of the wall, which serves to kind of push you away from the obstacle that you're worried about. And the design process for the prop guard and just for the entire vehicle begins in CATIA, where you draw your parts, make sure everything fits together properly, and then you can run finite element analysis and get an understanding of the physical properties of the material, how it will react to different loading, and then you can actually go out, prototype, and flight test. So this is an example of one of our durability tests. And you can see, like I discussed, it bounces off of the wall and is able to maintain stable flight and land safely, which is what you really want when it comes to bumping into obstacles in the environment. In addition to the structural component, we also have done custom circuit boards, and this is how we get all of our sensors to talk and play with each other nicely, and we also get power allocated where it needs to go. So this is a custom circuit board design. We design them ourselves, ship them out to get printed, and then when they come back to us, we populate them and test them ourselves and iterate as necessary. And the benefit to doing your own circuit board is that it's streamlined for what you need. So if you buy off the shelf, there's some general features that you don't need, that's extra mass for no reason. So doing it in-house allows us to ensure that it'll mount properly with our vehicle, but also that there's no dead weight, any vestigial organs kind of thing. So there's a lot of benefits to doing it in-house. And the circuit board is key to getting all of these sensors and processors talking to each other. So the main payload, sensors-wise, is a Kuyo laser, 2 cameras right now, and a PX4 optical flow sensor. So the laser, because it's an open environment, is no longer used for localizing, but instead is used for obstacle avoidance. So the laser will be constantly looking for the obstacles in the environment and feeding that information back to the atom, which is running high-level obstacle avoidance algorithms. So if it sees something, it'll make sure that the vehicle is able to plan to go around that object instead of running right into it. The cameras, the 2 webcams are used for localizing, so they identify lines of the arena, figure out where we are in the arena, and also allows to determine which ground vehicles are inside the arena or outside of the arena, and also if we're inside the arena. And then the optical flow sensor is used for determining velocity, and so it replaces the lasers from past competitions, and it gives us velocity feedback. And that goes and talks to the embedded system microprocessor, which controls the motors. So the cameras and the laser is used to determine set points in the environment. That's piped down to the microprocessor, which also is running the controls algorithms. And so that needs sensor feedback from the velocity from the optical flow sensor, and that finally gets turned into motor commands. In between the processor and the motors is a kill switch, so that if it's out of control, we can flip the switch, completely kill power motors, and fall out of the air pretty much immediately. So we have complete control in case Wi-Fi is lost or something. Well, we don't really need Wi-Fi, but in case something happens. And so if you kind of consider all those physical systems and roll it up together, this is the final product basically. So it's a very capable and durable flight vehicle. It's agile and it's strong, which is really what you need for this competition. So then if you get into the algorithm side of things, we are doing a Kalman filter on all of our signal filtering, and this is just it combines predictive modeling with sensor feedback, and it really cleans up the noise that you're operating on. So you can see in this situation, the red is the, okay, it does show up, it didn't before. The red spiky lines is the raw sensor data, and that's what's coming back because no sensor is perfect. You'll get a lot of erratic noises just from the environment, from the sensor itself. So if you combine that data with physical knowledge from your sensors of where you are in terms of velocity and orientation, you can do physics based on your physical properties like your moments of inertia and your mass and kind of predict where you should be in the next time step. So you balance where you should be with your sensor data, and it really cleans up that noise. So it's a predictive modeling approach to cleaning up filtering noise. And that just really helps the controls algorithms because your sensor data is what's keeping you in the air. So if you can clean that up, it makes your controls a lot smoother and a lot less jerky. Another high-level algorithm that's key to our success is obstacle avoidance. So this is still last year's vehicle, but the algorithm is the same. Basically, if you give the vehicle a set point, you can just tell it a spot in space where you want it to go. And then from there, the vehicle will make set points around that are safe. So basically, the laser is used to find obstacles in the environment and generate a cost map. So the vehicle knows where it wants to go, and a high cost is associated with dangerous objects like trash cans, and a low cost is open air. But very long paths also have a high cost. So by optimizing the cost of a path, you can optimize the safety and the speed of a path. And that's a very tunable system so that if you think it's still getting a little bit too close to things, you can up the cost and tune that on the fly. So that's a very modular system that's easy to change on the fly as you see fit. So for localizing, we've implemented line recognition and corner recognition. Line recognition is important for this competition because it's been guaranteed that the outlines of the arena will be squared and that there's also grid lines within that. So line recognition is essential to identifying where the arena is and whether or not we're inside the arena and whether or not the ground vehicles are inside the arena. So this is critical to determining where we are with respect to the actual boundaries of the arena and the goal line, of course. And we've also implemented corner detection, and this can be used for localizing. So they're basically the features that we keep track of. So if you find corners in one picture, move a little bit, and then take another picture and find the same corners, by determining where they are in the next screenshot, you can estimate velocity. And so corner detection is good for getting feedback on how you move with your environment. And so that brings us to this year's strategy. So we've actually adopted a 2-year approach to this competition. Year 1 was very focused on, well, first off, we will be implementing manual flight this year. So the emphasis was on structural design, and then our plan is to fly manually and acquire as much data as possible in terms of camera logs and laser logs, and use those for algorithms, for running simulations on our algorithms for the next year. So the most emphasis was on structural redesign because it's a completely new competition and there's no mass limit. We started from scratch with that. And we also implemented line and corner detection, and we need to validate that software before we move on. So this year is, we've done pretty much half of the work. We need to validate all of that and save data that will help us develop the rest of the way. So in year 2, we'll be making modifications to the airframe, making it as lightweight as possible, taking off mass where we can, making things more easily manufacturable, more easy to put together. And also, we're going to need to implement ground vehicle recognition and then ground vehicle prioritization. So now that you know which vehicle, where the ground vehicles are, which one do you go for first, and then how do we actually interact with that. And that's kind of the last step because we think it'll probably be a little bit easier to implement than the hardware algorithms. So our plan this year, again, is to just use RC control to navigate the arena, collect as much data as possible for future simulations, really analyze and determine the flight performance, see if it's where we think it should be for this competition, and possibly interact with the ground fleet manually to determine their sensitivity to maggots. So At this time, I'd like to take a moment to thank all of our sponsors who have made this possible by generously funding our team. And I'd like to thank you all for being such a wonderful audience, and I will take questions. Yes?
Two questions for you. First of all, what made you choose carbon fiber versus either Kevlar or fiberglass for components that require large energy reflections, such as your bumpers? My second question is, what is the actual control algorithm type that you were using for primary flight control?
Okay. In terms of carbon fiber, we honestly went with it because it's what we have a lot of still. We've got a lot of experience working with it from past designs, and we've still got a lot left. So we've decided to keep what we've got because we have so much extra. In terms of the flight controller, we're running a PID control on XY, and we've also got a DJI on board that runs kind of inner loops. So we've outsourced some of that just because it cuts some of the work out, but we plan on writing our own adaptive controller once we get XY completely straightened out. Yes?
By the way, impressed with your effort this year. The paper was great.
Thank you.
I did have a question about one term, and it's just my ignorance, you help me out there.
Sure.
Depth camera,
Okay.
what is that?
I don't remember the context of that.
It says, height is tracked by using a depth camera.
Okay, so it's a camera that's also accompanied with a sonar. So it's just a eye detector. It's a ping sensor. So it just, does a little sonar and finds the ground that way.
Okay, and just to clarify, you won't be flying autonomous this year at all?
No, not this year. Yeah, manual flight. We'll get more data that way, so it seems more valuable to us. Because we'll be able to simulate more of it manually and use that for future simulations. So data's key.
Looking forward to seeing that.
Yeah, thank you.
That's great. Okay, so you're going in knowing that you're going to come out with no score?
Yeah,
So-
yep. It's
You're
okay.
aware of that?
Yeah.
Okay.
We have no illusions. This is the autonomous robotics challenge.
Good paper, good presentation.
Thank you. Any other questions?
That's good.
Okay.
Please hang around.
Oh, do you have your vehicle with you?
Unfortunately, we left it in the van, but we could probably go grab it.
So either, basically after the presentation,
Mhm.
bring your vehicle in for the checkout.
Yeah, we planned on that. We have it with us, just not in this room. Okay. Thank you.